So we'll come back to that. Does anybody remember the 3 types of probability? Okay, so we'll say the expert says. So example of expert says is like, is a 10% chance of rain today. Okay, that's an expert's opinion based on a bunch of other stuff. No particular order. Anybody remember another one? Empirical. All right, what's empirical? What's that? Based on observations over time, yep. Okay, what's the third one? They're all ratios. Theoretical, yes, theoretical. Theoretical, there we go. And theoretical is based on knowing all simple events. And their respective ratios. Uh-oh. All right, so I'll give an example of each of these right now. And I'm going to go with first theoretical. So I'm going to roll a 6-sided die. Outcomes are in the set 1, 2, 3, 4, 5, or 6. Oops, curly bracket. So the stuff we learned about sets and Venn diagrams is going to be very important to us here. And so then the probability of rolling a 1, I would abbreviate with that notation right there. So let's see, how many 1s are there on the die? Well, there's 1 of them. And there's 6 possibilities. Now this is based on the following beliefs. Or a single belief, I guess. That the die is fair. So that means, oops. That's supposed to say IE. I messed that up. Oh shit, that's not the eraser. There's the eraser. And a circle. Let's get rid of the circle. Oh, come here. There you go. Trash can. Oops, IE. Each outcome is equally likely. All right. So the other day we were tossing around these cute foam dice. Catch. Toss it around your hand a minute. Does it feel like it's like weighted to one side or edge or corner or face? Does it feel like we're losing some pain? So that might make it a little bit unfair, but maybe not. So generally when we're talking about things like this, we believe that we're just as likely to get a 6 as a 4, okay, or a 1. Yes, Kelly? Yeah, it looks like somebody has chewed on some of these. I know. I had to get some new ones. Okay, so other theoretical situations like flipping a coin, for example, picking something out of a hat, like names or a drawing kind of thing. Those are all ideas like theoretical probability. Empirical are my spreadsheet is example of empirical probability. So on this particular spreadsheet, I have 242 die rolls. Actually, I'm only looking at 240 of them at the moment. And I counted here that 36 of those 240 rolls were ones, 40 of them were twos. So according to this data, the chance of getting a 1 is 36 out of 240. That's the empirical probability based on my data. So sometimes there are situations where we really can't come up with a theoretical probability, that we have to run a bunch of trials, write down the results, and then count. So all probabilities involve kind of the same thing. So empirical is where I observe and count. Okay, so in this case, roll dice 240 times, and then we count the ones. And so I counted there were 36 ones. And I could count the twos also. I can't remember how many twos there were. Was it 42? 41. Okay, and so on. So according to my observations here, the probability of getting a 1 is 36 out of 240. The probability of getting a 2 is 41 out of 240, and so on. Yes, those are empirical probabilities. So an example of when I might want to use an empirical probability, when we were playing around in class the other day, I was making believe I was Michael Jordan, and I was trying to shoot my foam dice into the basket over there, and I missed. Apparently I'm not Michael Jordan. And I try again. So what are the possible outcomes here when I'm trying to throw something into the basket? Well, what are the outcomes though? Forget, don't go in 50, don't give me probabilities yet, but it's either in the basket or it's out of the basket. That's all I'm concerned with, right? So there's two outcomes. And so then the question is, well, are they equally likely? Right, so we have a basket, we have Gary shooting into the basket, and the outcomes are in or out. And so the big question here is, are these guys equally likely outcomes? And we might say, well, yeah, there's two outcomes. They, you know, maybe 50% chance it's in, 50% chance it's out. If that's always the case, then it wouldn't matter if I went and shot hoops with Michael Jordan, because we each have the same chance of getting it in. Right? And we all agree that's nonsense. There's no way I could match up with him, even if he is wicked out of shape. Because he has a lot more experience. So they're not equally likable. Then how do we assign a probability to Gary's chance of getting in? And the only way to do that is to watch him do it a whole bunch of times and write down how many times he got it in, how many times he got it out. Then I could do it. So there are a lot of situations where there's no possible way to do it but empirically. Experiment, count, and then you get it. The last one is the expert's guess. And the expert's guess is usually based on theory and practice. Okay, and so a classic example of this one is a 10% chance of rain. What the hell does that mean? Okay. What that usually means to someone that says that, that's a meteorologist, is that on 10% of days similar to today at this moment, it rained. The other 90% of the time, it did not under the same or similar conditions. And they determine that with two things. One, they have lots of observations. And now they have computer models that they run simulations with. And the combination of those observations and computer models allow them to make that prediction. And the computer models use both theory and practice in making that happen. So they roll all out together, and the expert looks at it and says, looks like it's in the 10% range. Okay. And it's some kind of wild ass guess, but there's often theory behind it. And there are people that this is all they do is they just make these probability guesses. Like in insurance, anybody have any kind of insurance? Okay, insurance, the premiums are set by a group of people, some of which are mathematicians called actuaries. And they study populations of people and look at things like, you know, age, whether they went to school for a long time or not, where they live, what kind of job they have. And based on all that data, what's that? Yeah, because the probability of getting in a wreck before then is super high. You know, so they have tons of data on this. And that's how they come up with premiums for all kinds of different things. They study trends in the population. Yes. Yes. Yeah, there's really no way to be completely sure about anything like that. Yep. There are very few things we can say with 100% certainty or that zero certainty that it can't happen. Okay, so other things about probability, reminder, any particular probability has to be greater than or equal to zero, right? Zero meaning can't happen. And less than or equal to one meaning must happen or did happen. Like, what's the probability you're going to get a grade in this class? 100%. Yep, you're here, you're getting a grade. Okay. Yeah, what kind of grade, we have no idea, but you're going to get some kind of grade, right? So that's an absolute, it must happen. Other thing we talked about is the sum of all simple events and I'll define simple in just a second, is 1. 1 being the same as 100%. Okay. Like flipping a coin. We think it's 50% chance of head, 50% chance of tails. Heads and tails are the only simple events. 50% plus 50% is 100%, right? So examples of that, if we flip a coin, 50% plus 50% is 100%. Rolling the dice, whether I get a 1 or a 2 or a 3 or a 4 and so on, it's always theoretically believed to be 1/6. I got enough there. So all the simple events have to be 1. So sometimes it's easy to decide what a simple event is, other times it's not. So let's talk a little bit more about what a simple event is. The big thing there, nothing in common with any other event. Okay, that's an idea. Anybody know the other name we have for that phrase, nothing in common? Mutually exclusive, good, yeah. So that's what mutually exclusive means. Usually we use that for 2 different events. So events are mutually exclusive if they have nothing in common. So that's an important idea in playing around with probabilities. So the question is, okay, is rolling a 1 fundamentally different than rolling a 2? All right, there's a 2, here's a 1, they're different events, right? Okay, how about rolling an even number versus rolling an odd number? Are even numbers different than odds, or there's some numbers that are even and odd? They're totally different, right? So these guys are definitely mutually exclusive. What about an even number versus a prime number? Are they mutually exclusive events, or do they have something in common? An even number, can you give me an example then of a prime number that's even? 2. Yes, it's the only even prime number, right? So these guys are not mutually exclusive because they have 2 in common. So another thing about simple events, you know something simple if you can't break it down into smaller events. Okay, so that's another thing about simple. Come on, black. There you go. So you can't break down into smaller events. There was another big topic we talked about last time besides mutually exclusive, and at first we had a hard time keeping them straight because they seem similar. Anybody remember? Like I have 2 dice here, 2 die. This one is Fred and this one is Charlie. So I'm going to roll Charlie. Charlie gets 3. I roll Fred. Fred gets a 4. Did Fred and Charlie communicate about who is going to get what number? No, they did not. So the fact that Charlie got a 3 first did not affect Fred getting a 4? Okay, so they are independent of each other. They act independently. Yeah, so that's a big idea in probability, independence. Independent events. Oops, events. Okay. So independent events, that's where one event does not affect the outcome of another event. Okay, so examples of independent events, rolling 2 dice. Flipping 2 coins maybe? Forgot to bring change today, but if I flip a coin, I get a heads. If I go to flip the coin again, does the fact that I just got heads have anything to do with what's going to happen next? No. Just because I got a head doesn't mean I'm going to get a tail next. Doesn't mean I'm going to get a head next. I just don't know what's going to happen. Okay, how about shooting baskets? Are those independent? What do you think? Yes, no? I got a yes and a no so far. So Gary shoots. Oh, he missed. I'm getting nervous. I'm starting to sweat. I'm going to throw it again. Ready? Oh, God, so frustrated I missed. What do you think? Could I work myself up and just throw like a spaz the next time? Wrong direction. Oh, my God. Hate that. Okay, so the coins don't have emotion, neither do the dice, but me throwing this in, I might get on a roll, and then I'm definitely going to get the next one in. I'm going to get another one in, right? So I could get on a streak, positive or negative. So I'm going to have to say shooting baskets is probably not a group of independent events. Where's my magic pen? Oh, there it is. So we're going to strike that from the record. Okay, so it's not always safe to assume events are independent. You always have to think about, are events mutually exclusive? Are events independent? You always have to think about that. Usually mutually exclusive comes up when we're trying to add probabilities, and independence comes up when we're trying to multiply probabilities. Okay, anybody ever play cards here? A little bit? Little 21, okay, yeah. War, I love, you know what's fun? Did you ever play multiplication war or addition war? You each throw down a card, and if it's multiplication war, you have to say what it multiplies out to. And the first one who says it wins. Can you really? Oh, geez. Okay, let's see. What am I looking up here? I forgot. Oh yeah, I'm going to Google and I want random cards. And random.org has a great website. Ooh, they have a random card shuffler. Okay, let's see. Number of cards, draw one card. Okay, so just let's get this out. There are 4 different suits in a standard deck of cards in this country, and they consist of aces, 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, 10s, and then jacks, queens, and kings. So there's 13 individuals in each suit, 4 times 13 being 52, right? If we throw in jokers, we have 54, but usually there's 52 cards in the deck. Okay, so like, what's the probability of getting the Queen of Hearts? 1 out of 52. Okay, so I have some cards, right? And I pick one. I'm not going to show anybody. I'm not even going to look at it. What's the probability the card I picked is the Queen of Hearts? Okay, so now I'm going to draw a second card. What's the probability that second card is the Queen of Hearts? Yeah, so the denominator changes, right? It goes from 1 out of 52 to 1 out of 51. Okay. But that's a little complicated because what if the other card in my hand already is the Queen of Hearts? Then yeah, so but I don't know what it is, right? So probabilities get complicated quickly, and if I draw cards and I don't put them back in, that means the next card depends on what the first card was. They're not independent events. The only time with cards you get independence is if you put the card back in the deck, which doesn't happen with card games. Okay. So when we're doing things with card games, events are always dependent, never independent, which makes them very hard to count. All right, so this is a cool website. Let's just see what they give us anyway. Let's suppose I'm going to get 5 cards from one deck. Let's see, show remaining cards face down. Okay, let's see what happens. Draw. Isn't this cute? Yeah, there's my 5 cards. There's the other, how many cards are left? 47, thank you, good math. 47 cards lying there. It's kind of cool. What happens if I hit again? Does it give me another 5 cards? Oh no, it doesn't. It just redoes the whole thing. Huh. Okay, cute. So now let's get back to the dice for a minute. So other idea I wanted to play with, where's my dice? There's my dice. So here's, I'm gonna get rid of those last 2 because they're bugging me there. Sorry, Garth. Okay, and so the last 6 columns here were generated by people in the class. These columns right here, I used a random function called rand between. TI calculators can do that. Every spreadsheet can do that. So I said, give me random numbers between 1 and 6. The way Excel does it, every time you actively do something on the screen, it reshuffles those random numbers, which is kind of a pain sometimes. There's a way to turn that off, but I don't feel like doing it. So it reshuffled some of mine, and now I'm down to 34 ones, 41 twos. It shifted a little bit when I did that. So one kind of neat thing, I'm going to copy all this stuff into Google because Google does a better job of drawing pictures of numbers. Sorry, Microsoft, you do some things well. Let's get to my drive. And let's see, do I have a Math 212 folder? I do. Let's add a new spreadsheet to it and paste all these lovely numbers in. And then I'm going to ask Google to make a chart for me. So I think there's a button here for that. More charts. And Google looks at my data and it tries to make this funky line chart. And I think I want this chart over here. Ooh, interesting. What the heck is it doing? Huh. More charts. I do want a bar chart, but I like this one. Let's see if I can make this one work for me. Let's customize it. And bucket size. Let's say bucket size is 1 maybe. Let's see how that affects it. That didn't change anything. I thought it might. Omit item dividers. What's that mean? Ooh, that's cute. Bucket size, bucket size. Huh. Oh, I see. It's counting each column separate. How do I get it to count them all together? I want one giant data series. Oh, it doesn't like that they're in different columns. Bummer. Okay, let's cancel that. All right, I thought it would do a better job. If I can make Excel do it. What I was trying to do is have it make you guys know what a histogram is? A histogram is when you group numbers, like say, count all the ones for me, count all the twos for me, count all the threes for me. And it's basically a bar chart. What's that? I could just make a graph of this right here. So, but I was trying to get it to do it for me so I didn't have to do all that work. That's a good question. So if I do a bar chart, based on these numbers here, that's just a regular histogram. If I do it on the percentages, that's what's called a frequency histogram or a relative frequency histogram. Actually, it's a relative frequency histogram where we go off percentages instead of actual numbers. And so I think I want to do the relative frequency histogram. So let's see if Excel can do what I want. Oh yeah, perfect. I want that one right there. Okay, so there's the chart. And here's the cool thing. If I go and I do this, I can reshuffle my random numbers. Gives me a slightly different one each time. Now it's only changing it a little bit because only 2 columns here are randomly generated. Okay. What should I expect this histogram to look like? Should it have a bell kind of shape, a U kind of shape, a flat kind of shape? It should be flat because I'm expecting about the same amount of ones as twos, as threes, as fours, as so far. So when we're playing around with probability stuff, histograms are super helpful. Okay. The theoretical histogram for a 6-sided die is flat. 1/6, 1/6, 1/6, 1/6. The empirical one's going to be a little bumpy. Okay. All right. So let's see. One more thing to put on the video, then I'm going to stop the video and do something else with you guys. So that idea I was just talking about, empirical versus theoretical. Sometimes there just isn't a theoretical probability to go with something. It just doesn't exist. Okay, and so we're just stuck with empirical. When there is a relationship between them, we have an idea called, again, the law of large numbers. And basically what the law of large numbers says is that the larger group of observations you have, group, the closer we get to the theoretical probability. Another idea related to the law of large numbers, related to probabilities, is an idea called expected value, which I just want to go over quick, and then I'll stop the recording. And there's a few different versions of expected value. We're just going to keep it pretty simple for now. I rolled 240 times. I expect to get blank ones. How many ones do I expect to get out of those 240 rolls? About 40, right? Where do we get that 40? Well, I expect 1/6 of the 240 to be ones. All right, so if I take the probability times the amount of number of observations, that gives me what I expect to have happen. Will I get 40? Probably not. Will I get close to it if I do enough samples? Is 240 enough to get close? Well, depends on what you mean by close. Right, so that's one thing about the law of large numbers. There's a couple of fuzzy things. What does it mean to have enough observations, and what does close enough mean? Okay. So looking back at my table, let's see, I had it in Google here. From table, that view zoom 200 go. Okay, is 35 close to 40? Whoa, that's scary. Is 46 close to 40? Is 29 close to 40? All right, I'd say 35 is kind of close. It's 5 away. 29, is that close to 40? Let's stretch it a little bit. I might need more than 240 samples because that's kind of scaring me. So I could run more if I needed to. Okay, so here's what I want you to do next. I'm going to stop the recording here. That's just a review of the basics of probability.